So a group action on a set, remember, is a map that takes an element in a group and an element in the set to another element in the set. And which satisfies various axioms. The identity acts trivially on the set, and it has an associative action. We saw that if we had a point in S, we could define its orbit, O of S. We could define its stabilizer, G of S, which is a subgroup of G. O of S is a subset of S. And we saw that the orbit was identified as a set with the set of cosets of the stabilizer. And moreover, that if you took another point S prime in the orbit, so it was of the form G of S, and you looked at what the stabilizer of S prime was, it was a conjugate subgroup. Conjugate subgroup. And so we saw last time that the notion of a transitive action, a set on which G act permuted all the elements from one to another, like an orbit, could be identified with a conjugacy class of subgroups, because here is an example of a transitive action, and an abstract transitive action is always identified by this. This identification is easy. You take a coset, GGS, and you take it to the image of S, which only depends on the coset. And you get all the elements that are translates of S, and you get all the cosets. So that's a pretty simple notion, but it's very powerful because it tells us that all transitive actions of a group can be built up internally from the group, from its subgroups. It also has the following property. Suppose G acts on S, and the order of G and the order of S are both finite. With orbits O1, OS1, OS2, OSN. So the first thing is there are only finitely many orbits, because there are only finitely many elements in the set. So there are fewer orbits than there are elements in the set. The worst possible case is that every element is in its own orbit. And then the order of S is, of course, the sum of the size of the orbits because the set S is itself decomposed as a disjoint union of the orbits for G. So if you add up the elements in the different orbits, you get the total number of elements in the set. But because of this property that every orbit is identified with a coset, and we know the order of a coset is the order of G divided by the order of the stabilizer, this can be written as the order of G divided by GS1 plus the order of G divided by GS2 plus the order of G divided by the order of GS sub n. In particular, the order of S is written as a sum of numbers, all of which divide the order of G. So this could also be written as the order of G times the sum 1 over the order of GSI, the order of the stabilizers. I is equal to 1 to n. So that's called the counting formula in the book. They really break it into two formulas. One, it says that this order is the order of G divided by the order of the stabilizer. And the other is that the order of the set is the sum of the orders of all the orbits. So this has a number of very, very powerful applications, this simple counting formula. Most of our results on finite groups, in some way or another, come out of this counting formula, applied in various situations. So let me give you an example. Suppose you have a group which is finite, and you have two subgroups, H and K. And then you have their intersection, of course, which is a subgroup of both of them. Okay? So I'm going to prove for you, then, proposition, the index of K and G that index is greater than or equal to the index of H intersect K in H for any subgroups H and K. So we view H intersect K as a subgroup of H, and K as a subgroup of G. This index is always greater than or equal to that index. Okay, proof. Let S be G mod K, the cosets of K in G. So the order of S is the index of G and K. We know that. Now G acts transitively on S. You can get from any one left coset of K to any other left coset of K by multiplying by an element in G. But we can take the restriction of this action to H. Can restrict the action of G on S to the subgroup H for any subgroup, and you get an H action. One of the definitions, a consequence of this definition of when G acts on a set is if you have any subgroup of G, H, and you have an action of G on the set, and you restrict that action to H, that gives you an action of H on the set. It satisfies the same axioms. Now, there's no reason any longer for H to act transitively on the set of K cosets. No reason. So this action is a sum or a union of H orbits. And we're going to show that this is the size of one of the H orbits. And in particular, the size of the set is given by the sum of the sizes of the orbits. So in particular, the size of S is greater than or equal to the size of any orbit. That's how we're going to prove this. Well, what orbit has the size H mod H intersect K? Well, let's see. Consider the orbit of the coset just K under, well, I could call it EK, under the action of H. This is one element in my set. Well, the orbit of S is identified with H, this is under H, modulo the subgroup of H that stabilizes S. What is the subgroup of H that stabilizes S? This is the set of little h in H such that HK is equal to K, which is exactly the elements in H which are in K. And so the size of this orbit under H is exactly the order of H divided by the order of H intersect K. And that shows that the size of the set is at least as large as the size of the H orbit for any two subgroups. Okay? So that was sort of a mindless counting argument. It looks complicated, but it isn't any more complicated when you work it out like this. Let me give you another proof, which we'll come to a little later, which involves a particular G action on itself. So all these, we saw that we have a transitive action of G on itself by left multiplication. G acts transitively on S equal G by left multiplication. Namely, G of an element S in G is G times S. Because we can get to any element by left multiplying the identity by something. The orbit of the identity element is all of G. But there is a more interesting action of G on itself by conjugation. And here the action is that G of S is equal to GS G inverse. This is a new element of the set S, right? And you have to check that it's an action. So the identity takes any element of the group to itself, because the identity commutes with the, right? So it gives the identity. And if you take GH of S, that becomes G of H of S. Again, if you first conjugate by H and then conjugate by G, you get conjugation by GH. So it satisfies the axioms. However, this is not a transitive action. You can't get, unless the group is the trivial group, because the orbit of the identity element is what in this action? Is itself. Very good. The orbit of the identity element in this action is equal to E, and the stabilizer of the identity is all of G. So you can't get from a non-identity element to the identity element via this action. You cannot conjugate some element which is not the identity into the identity. Consequently, it's not a transitive action. They're different orbits. The orbits are called the conjugacy classes. It's by definition. That's the definition of a conjugacy class of S. And the formula we wrote before would say that the order of G is equal to the sum over the conjugacy classes, the size of the orbit of S, which can also be written as the sum over the conjugacy classes of G, the order of G, divided by the stabilizer. Now, what is the stabilizer of an element here? Well, G would fix S if this is equal to S, which means that G commutes with S. That's called the centralizer of S. G in G, such that GS is equal to SG. It's called the centralizer of S. So that the order of a group is you take the different conjugacy classes in the group, you take the order of G divided by the order of their centralizer. Here's a particularly weird example of this. Weird. Suppose my group is abelian. Abelian. Then this element is equal to S for all G and G. Because G commutes with everything. Everything commutes in this group. Consequently, in an abelian group, these orbits have one element in them. Every element is in its own conjugacy class. So if G abelian, every orbit has one element in it. And there's no break of G into conjugacy classes at all. Each conjugacy class is just a singleton. The centralizer, GS, is G. And this just says that the order of G is the sum of 1 G times. That's not so interesting. But if you take more interesting groups, this becomes an interesting identity. It's called, by the way, the class equation for a group, that the order of a group is this sum. This is sometimes called the class equation. So, for example, let's take a look at the symmetric group on 3 letters, which is our first non-abelian group. The symmetric group on 3 letters has the identity that commutes with everything. That's one conjugacy class. Another conjugacy class is the elements of order 2. So those are what we call transpositions, things that fix something. So an example of a transposition would be this. Or the things fixing 2 and switching 1 and 3. Or the things switching 3 and switching 1 and 2. So there are 3 elements of order 2. They form a conjugacy class. And then there are 2 elements of order 3. And they are all, so those things look like this. Those are the things that cycle around. We're going to, by the way, once we get a little bit further, we're going to determine all the conjugacy classes in the symmetric group. But in S3, there are three different conjugacy classes: the identity, the elements of order 2, the elements of order 3. The class equation looks like this. 6 is equal to 1 plus 2, 3 plus 2. Here, the centralizer is just the element of order 2. Everything commutes with itself. Right? And here, the centralizers are the subgroup of order 3 generated by the element. Here's ZS E of order 6. Here Z of a transposition is of order 2 and is the subgroup E and tau. And here Z of an element of order 3, let's call this element sigma. Z of sigma is the subgroup E sigma sigma squared. So that's the class equation for the symmetric group of order 3. It's very interesting, given a group, to determine its conjugacy classes. It's more intrinsic for a non-abelian group to know its conjugacy classes than to know its elements. Because in a group, things are always confused by this question of conjugacy. We already saw for group actions, it really isn't the subgroup which is the stabilizer, because that depends on which point you choose in the orbit. If you chose a different point in the orbit, you'd get a conjugate subgroup. So frequently you want to consider the set of an element in the group up to conjugacy. So that's knowing what is the set of conjugacy classes. Here, there are three conjugacy classes. We're going to do conjugacy classes in the symmetric group. And we're going to show that the order of the symmetric group turns out to be n factorial. But the number of conjugacy classes turns out to be the number of partitions of n, which is much smaller. And the fact that there are a smaller number of conjugacy classes and elements allows you to work with a group. But one of the most interesting finite groups that's been discovered, and there are many cosmological models of the universe based on it, is called the monster group. So I'll talk about the monster maybe later in the course. But the monster group is a finite group that was discovered essentially on the computer in the 1980s, which has order about 10 to the 47th. So about the number of particles in this room. You can't write down that group. You cannot store the elements of that group anywhere. However, we know an enormous amount about this group because it has less than 200 conjugacy classes. It's so non-abelian that the elements get quite conjugated into each other. So we can work with the monster group because we work with its conjugacy classes. So those of you who know the difference between, there's estimates in mathematics between the size of n factorial, that's Stirling's formula, and the size of the partition function. This is considerably smaller than this. And that reflects the non-abelian nature. In an abelian group, you get no advantage. In the abelian group, the number of conjugacy classes is the number of elements. Okay. I'll give you another example of this amazing class formula. Now, when is an element in a group, when for conjugation action, when is the size of the orbit of S equal to 1? That's a good question. Well, we know that this size of the orbit is the order of G divided by the order of the centralizer. So this is equivalent to the condition when is G sub S equal to G? When, as the centralizer, the full group. Well, the centralizer we saw was the set of elements which commuted with S. Right? So the centralizer is the full group, says that every element commutes with S, which means that S is in what we call the center of the group. That was a canonical normal subgroup of the things that commuted with everything. So in this formula, there are a certain number of terms which have ones. For example, the identity element is always a 1. There may be more. And the number of such elements is the order of the center. So here, we only had one such element, because in the symmetric group, if you're not the identity element, you're not in the center. We're going to prove that later too. There's no more center of the symmetric group except the identity element once n is at least 3. But I'm going to prove to you an amazing thing that you get out of this little formula here, which is that if the order of your group is a prime power, it has a non-trivial center. If the order of G is equal to p to the n with p a prime, then the center of G is not equal to the identity element. Namely, you have non-trivial elements in the center of the group. Okay? So that's not true when we had order 6. But if I had a group of order 8 or order 16 or order 32, any group of that sort has to have a non-trivial center. Why? Because look at this formula. Every term in this formula divides the order of G. The divisors of the order of G proof. These terms have order p to the k with 0 less than or equal to k less than or equal to n. Okay? In particular, they're all divisible by p except when k is equal to 0. When k is equal to 0 and the size of the orbit is equal to 1. I mean, one possibility is the centralizer is the full group. Okay? So all the terms here except the central conjugacy classes are divisible by p. Over here, the order of G is divisible by p. So the number of 1s that we get in this sum has to be divisible by p. Which means you can't just have the identity in the center. 1 is not divisible by p. Is divisible by p. And consequently not equal to 1. And that proves that the center is non-trivial. So it's a purely divisibility argument, which we see fails for groups of order 6. But for any group of prime power order, it works. And this gives a very powerful way of analyzing groups of prime power order. Why? Because the center is a normal subgroup. So if G of prime power order and Z is equal to its center, then the quotient group G mod Z, let's call that group G1, also has prime power order. And therefore, it has a non-trivial center. And then you make the next quotient, G2 is equal to G1 mod Z1. Same thing, continue down until you get to the trivial group. You're getting to a smaller group each time. A strictly smaller group, because this center is, which is not equal to the identity element. So this has prime power order less than the order of G. And this has prime power order less than the order of G1. Same principle. Its center, which is not equal to the identity. And so we have an inductive procedure starting with a group of prime power order and taking the quotient by its center and continuing of eventually getting down to the trivial group, because eventually we get down to a group which has order less than p. Right? And so we can then build our group up from these particular centers. And that's a complicated process. But abelian p groups we understand, or at least we pretend to understand. So it gives a way of breaking a group of prime power order. It shows, for example, it can't be simple. Let's put that down. So G is not simple. Unless the order of G is equal to P, it turns out. Because you can, if it's an abelian group, you take any subgroup, and well, I have to prove that there's any subgroup, but I'll just put this in parentheses because we haven't proved it yet. I mean, it's possible the center is the entire group. But if the center is not the entire group, we've constructed a non-trivial normal subgroup. Yeah?
Does simple mean?
Simple means no non-trivial normal subgroups. No non-trivial. The only normal subgroup is G or the identity. So here, you see if you have a group of prime power order and you take its center, that's a normal subgroup. It's not the identity. So the only thing that would be a problem here is if the center were the entire group. If the center is the entire group, the group is abelian. Okay? If it doesn't have order P, I can produce in an abelian group of order P squared or P cubed or P to the fourth a non-trivial subgroup. And then any subgroup of an abelian group is normal. Yeah?
That's not an if and only if implication, right? If the center... Sorry.
Oh, no, it's not if and only if. I can make abelian groups of any order because we could make cyclic groups of any order. So a cyclic group is equal to its center. But the amazing thing is only knowing something about the order of a group allows me to conclude something about its center. So if I'm going to make simple groups, they have to involve several primes in them. In fact, a very famous theorem that was proved at the beginning of the 20th century by Burnside said that if you make a simple group, it can't even be the power of one prime times another prime. So Burnside, this is just an aside, much harder theorem than this, proved that if the order of G is P to the n times Q to the m, then G is not simple. But on the other hand, we're going to see that A5, that's going to be our first non-abelian simple group, is a simple group of order 60, which is 2 squared times 3 times 5. So once you add 3 primes, you can do it. So the order of a group is going to say something about the existence of normal subgroups. Okay, now I want to do the counting formula in another case. You know, here in this conjugacy class argument, we knew the order of the group, and we deduced something about the size of conjugacy. Like, for example, here we deduced that there had to be conjugacy classes of size 1. Now, you could sometimes turn this class equation around, know something about the orbits, and deduce something about the order of the group. Okay, so I'm going to show you how that works. So a good formula should be able to read both ways. And frequently, some of the greatest mathematics that's ever done is taking a formula that's being read one way and turning it upside down. And saying, well, let's suppose we knew all about the orbits. Can we get the group back? So I'm going to do this for you in a famous problem of the groups that preserve the regular solids in R3. So we want to take a look at finite subgroups S, G, inside of SO3, the orthogonal group on 3 dimensions, preserving the regular solids in R3. We're going to come back to this a little bit more, but we'll start with it today. I give up. No more interesting pieces of chalk. Let's try this one. All right, now remember, what do elements in SO3 do? Well, they act on 3 space. They preserve the points in the sphere of radius 1 from the origin. So let's call this sphere S2. It's the sphere inside of 3 space. The reason I call it S2 is that the surface of the sphere forms something of dimension 2. Now, every element we showed in G, every G in G, is rotation around an axis. That was Euler's theorem. Namely, there was some basis of 3 space where the matrix of G looked like this. 1, rotation theta, 0, 0. Well, 0, 0, 0, 0. And the eigenvector, let's take you had some line through the origin that was fixed by the group. That hit the sphere in a north pole and a south pole. And then you rotated an angle theta in the plane perpendicular to that axis. Of course, the axes could differ for the elements in the group. So you got a non-commutative group because if you took one axis and you took the rotation around another axis, they wouldn't necessarily commute with each other. Whereas the rotations around a fixed axis commute and form a group like SO2. Okay? Now, we want to fix a certain regular solid in the sphere. So the first case I'm going to do is the tetrahedron, which is based on 4 points in the sphere. Let's see if I can draw it, and then I'll give you a better picture. We'll take the north pole, and then there's a triangle down at the bottom, an equilateral triangle. The tetrahedron touches the sphere. We're going to have it touch the sphere in 4 points. And you get 4 different triangles. So here's a better picture of the tetrahedron, which I put together with magnets. So you imagine the sphere going around. So the center of the sphere is right in the middle. And these points are the same distance from the origin, so are on the sphere. And the edges connect those points. So the tetrahedron has 4 vertices. It has 1, 2, 3, 4, 5, 6 edges and 4 faces. Four faces, and every face is an equilateral triangle. Okay? Here's the tetrahedron. Now I want to ask, what is the subgroup of SO3 that preserves the tetrahedron, namely all rotations of space that take this tetrahedron into itself? Into itself. Okay? Now I claim that that's a subgroup of the symmetric group on 4 letters. So that's more or less obvious. Because if it takes it into itself, it has to take the vertices to themselves. There are 4 vertices, right? So I claim that the G preserving tetrahedron is a subgroup of S4, namely the permutations of the vertices. It may not be possible to realize every permutation of the vertices from a rotation in 3 space. But if a rotation in 3 space takes the tetrahedron into itself, it takes the vertices to the vertices, and that completely determines the rotation. Once I know where these 4 points go, I know the rotation. Okay? Now, I'm going to show you it's a non-trivial subgroup, and I'm going to determine its order from that counting formula that I just erased. Okay? So here's why it's a non-trivial subgroup. Take the axis that goes through this point. This is your north pole, and is perpendicular to this triangle, so it passes through the middle of the triangle and it goes out the south pole. In other words, take the axis through the sphere that connects this point and the midpoint of that and whatever that's called in a triangle. Center of the triangle? Whatever. It's an equilateral triangle. They're all the same. Whatever word you use for it, it's the same word. So connect those 2 points via a line. That determines an axis through the origin. And take the rotations in that axis. And I claim you can do 3 rotations. You can rotate around 120 degrees, or you could do it square or its cube. And those preserve the tetrahedron. So there are 3 rotations around this axis preserving the tetrahedron. Okay? Likewise, for any other vertex, there are 3 rotations around the axis that goes through the vertex and is perpendicular. So there was nothing special about this vertex. If I started with this vertex and I took the axis through the vertex and the midpoint of that side and I rotated the tetrahedron around that axis, I'd still have 3 rotations that preserve the tetrahedron. Okay? In particular, whatever this group is of S4, it acts transitively on set S of vertices. Because just taking the 3 rotations around the axis going through here permutes these 3 vertices transitively. And if I want to show that these 3 vertices are in the same orbit as this vertex, I take, say, rotation around this axis, and that permutes these 3 vertices transitively. So I can get from any vertex to any other vertex with some element in this group. Okay? So that's the transitive action. So therefore, 4 has to be equal to the order of g divided by the order of g stabilizing a vertex. That's because this is the size of S. It's a single orbit. So that has to be the order of group divided by the order of the group stabilizing a vertex. But the order of the group stabilizing a vertex is clearly 3. Right? Because it has to permute these poor 3 things around. If I fixed one of them, I could never, then the rotation is trivial. So the only possibilities is a rotation through 120 degrees or a rotation through 240 degrees. So that's a group of order 3. So we get it's the order of g divided by 3. And that tells us from the counting formula that the order of g is 12. And it's a subgroup of this group which has order 24. Now it turns out, we haven't proved it yet, but it turns out there's only one subgroup of S4 which has order 12. And that is, you know 1, so why not tell me? If I tell you there's only one, what is it? A4, exactly. Only subgroup of S4 of order 12. We haven't proved that yet, although it's pretty reasonable. If you think about how it permutes the vertices, and you think of what possible things we're getting in this group, I claim we already see in this group the identity element. We know the identity element, and we can see 1, 2, 3, 4, 8 elements of order 3 fixing a single vertex. Because each vertex gives you, there are 3 elements here, but one of them is the identity element. So you get these 2 non-trivial rotations, and you get 8 rotations that way. So there are only 3 elements left in the group, right? So 3 elements left, because there are 12 elements in the group. And those elements all have order 2. And in fact, they fix an edge. Isn't that interesting? You see there are 6 edges. So the stabilizer of an edge, if this group permutes the edges transitively, and it does, the stabilizer of an edge has order 2. And those are, in fact, the different, the conjugacy class. Well, I'll do conjugacy classes later. So, and if you know the alternating group on 4 letters, you can't have a permutation like this in it. You can't have a permutation like this. Those elements of order 2 are not in the alternating group because that's an odd permutation. But you could have an element of order 2 that looks like this. The product of 2 transpositions. And that's, in fact, what these 2 elements of order 2 do to the vertices. Namely, it would switch these 2 vertices, and it would switch these 2 vertices. And I forget what edge it stabilizes at that point.
The left, or the right one.
This edge here?
Yeah.
If it switches,
It basically turns the tetrahedron upside down.
it turns the tetrahedron upside down.
But it fixes 2 edges, it's that one and the one that
It fixes both. Yes, you're right. It fixes both. If it permutes these 2 vertices and it permutes these 2 vertices, it fixes this edge, and it also happens to have the property of fixing that edge. And how does it turn the tetrahedron upside down? Never mind. That's why we have models. OK, I'll let you think about that. The next regular solid, yes, come.
Can you go over again what
A4 is? It's the subgroup of S4 consisting of the even permutations. It's the elements G in S4 such that when you view them as permutation matrices, the determinant of G is equal to 1, not minus 1. So that's a subgroup of index 2. This is a subgroup of index 2. Turns out to be the same group. When you go to the next regular solid, so you see, notice that this has the property that the faces are triangles, and we have 3 triangles around a point. Right? If you put 4 triangles around a point and you close it up, you get what's called the octahedron, because it has 8 vertices now. And if we try to determine its rotation group, well, if we take an axis through the opposite sides, vertices, we now have a rotation of order 4 around here. Whoa! That's the problem with magnets. Damn thing. Let's try again. I knew this would never work. Well, maybe it'll work. Let's see what happens here. 1, 2, 2, 2. Marvelous. It's going to work. It's going to work. What am I missing? I'm missing a... Oh, but that's okay. You can imagine that. Oh, never mind. Damn charge. This is the difference between physics and mathematics. What I used to hate about my labs in physics, I don't know if you guys do these labs. We'd have a lab where we'd like test the universal constant of gravitation, something like that. And we'd have these weightless things sliding around and dropping up and down, and we'd be timing them or measuring flashes of light or all kinds of cool things. And then you'd go home, right? And you'd write up your lab report, and you'd calculate the universal constant of gravitation, and it would be off by 7 orders of magnitude. So then, since you knew the answer, you'd start with the universal constant of gravitation and work backwards to what you should have observed. And then it would prove that, but that was too good, right? Because then the lab assistant would know. So then you'd have to move it a little bit so you'd get within 1 order of the universal constant of gravitation. Okay? So here we have an order element. If we fix this vertex, we have an element of order 4. And we can do that for any pair of vertices, their rotations. So that shows that it permutes the vertices transitively. There are 6 vertices. The stabilizer of any vertex has order 4, so the group has order 24. 6 times 4. 6 vertices, stabilizer of order 4. That turns out to be the symmetric group on 4 letters, the stabilizer of the octahedron. And it's a little hard to see which 4 things are being permuted, because as you notice, there are 6 vertices, and then there are 8 faces, and there are 8 edges, right? So it looks a little weird to try to find 4 things that are being permuted, but I'll leave that to you as an exercise. Pardon? Yeah?
This is probably a dumb question, but now that you have a model, when the stabilizing group of one of the vertices
Stabilizes. Now, okay, let's point that out. That can sometimes happen in a group action. For example, it doesn't make any difference. All we know is that the stabilizer of another vertex is a conjugate subgroup. But conjugation sometimes preserves the group. So for example, if I had a group action, so G acts, we saw on anything like G mod H. Suppose this is our set S. Suppose H is a normal subgroup. This is the most extreme case. Then GS is equal to H for all S. Namely, the same subgroup stabilizes every point in S. It's a conjugate subgroup, but for a normal subgroup, you don't move. So what happens is, and that's what's amazing, is the element in the group that takes this vertex to this vertex conjugates this subgroup of order 4 into itself. And that's why the stabilizer of this vertex is the same as the stabilizer of that vertex. But from the point of view of a counting formula, once you verify that you can get from any vertex to any other, and the first rotation group shows that you can get from any of these 4 vertices to any other, and then if I say rotate from here around here, I can get from this vertex to this one, and then down to this one, so I can get from any 6 to any other. Then the order of the group is the number of vertices times the stabilizer of the vertex, which is 4. So this group has order 24. Okay, final case. So the octahedron, or its dual, the cube. The order of G is 24. And in fact, G is isomorphic to S4, although I haven't told you what 4 things it's permuting, because we haven't gotten a natural set of 4 things here like we did here. Final case. You can put 5 triangles around a vertex. If you put 6 equilateral triangles around a vertex, you flatten out in the plane. But in space, you can still put 5 triangles around a vertex. I don't know if I dare to try. You think I can try? Why not? I'm going to try. This magnet isn't going to work too well. Forget it. If you put 5 triangles around a vertex, you get something called an icosahedron. It closes up with 12 faces. A famous Greek figure. So this has three triangles around a vertex. The octahedron has 4 triangles. And then if you put 5 triangles, you get the icosahedron, which has 20 vertices and 12 faces, all of which are pentagons. I'm sorry, which are triangles. I'm sorry, I'm going the wrong way. It's 20 faces and 12 vertices. Thank you. I'm going for the dodecahedron. Thank you. You're right. So it has 20 faces. It has 30 edges. You have to find a picture of this in a book. I'll bring it in next time, I promise, because I want to talk about this group more. Again, the finite subgroup of O3 that preserves the regular icosahedron permutes the vertices transitively, and since there are 5 things coming out of each vertex, you have a rotation of order 5 around each vertex. And that means that the order of the group is 12 times 5, which is 60, and it turns out that the group itself is the alternating group on 5 letters. Although, again, I can't tell you which 5 things are being permuted. That's a really, as I say, a very famous group because it's the first simple group. It's the first group without normal subgroups. We're going to prove that. And now I can tell you what I've been promising to tell you about the latest conjecture on the shape of the universe. Okay, so there's a conjecture put out by mathematicians which is going to be destroyed by the astronomers in about a month, but I still have a chance to talk about it. And it's that the universe is a closed shape, which is a 3-dimensional object. And in fact, the universe is the coset space SO3 modulo the stabilizer of an icosahedron. Namely, it's a coset space. Now you have to understand that SO3 is a 3-dimensional shape. Why is SO3 a 3-dimensional shape? Well, because SO3 acts transitively on the 2-sphere with stabilizer of a point isomorphic to SO2. Now SO2 is clearly a 1-dimensional group. It's rotations around an angle, and you have a choice of the angle, so that's a 1-dimensional group. So just as we have the counting formula that the order of a set is the order of a group divided by the order of the stabilizer, the dimension of a set is the dimension of the group modulo the dimension of the stabilizer. So 2 plus 1 gives a 3-dimensional group. So this, in fact, is a 3-dimensional shape. It's a closed 3-dimensional shape. And if you make the coset space by a finite group, you also get a closed 3-dimensional shape with very interesting what's called algebraic topology. This is called the Poincare 3-sphere. And the reason it was called the Poincare 3-sphere, it's very important in the history of mathematics, because Poincare was very interested in determining if something which looked algebraico-topologically like the 3-sphere, so here's the 3-sphere, it's in 4 space, of course. Those of you who have studied algebraic topology know that Poincare at the beginning of this century invented some invariants of shapes called homology. And the 3-sphere has the property that its 0 homology is z, its first homology is 0, its second homology is 0, and its third homology group is z. And Poincare proved that this weird shape had exactly the same homology as the 3-sphere. Exactly the same homology as the 3-sphere. What it doesn't have is what's called the same fundamental group, which is another invariant that Poincare defined. And the fundamental group here is trivial for the 3-sphere. And the fundamental group for this weird Poincare 3-sphere is a group a little larger than A5, which has order 120 and has quotient group A5. So that's called A5 tilde. And that allowed Poincaré to distinguish this space from the three-sphere because it had a different topological invariant, even though its homology was the same. So when you study algebraic topology, this is a famous example. Now, why are mathematicians trying to drag some famous example into the shape of the universe? Well, it would be nice. It would be nice if God used all these nice examples. But the astronomers are now testing out the background radiation data to see. This prediction predicts all kinds of weird things. Like if you look up at the sky over there, you see the same thing as if you look down at the sky down there. Things like that. And we haven't seen those things. So, but at least that's science. Science is, one of the great definitions of a scientific proposition by Karl Popper this century was something that's falsifiable. You can never prove it, but you can prove it false. That's the difference between a scientific statement and a statement about literature. Okay? So this is a statement that the universe has this shape as a three-dimensional object. So now we can test it and prove it false and then try to find something else. Okay? So we'll do more about the icosahedron next time.